Welcome to my channel Math Infinity. In today's video I will give you a complete proof of Banach Fixed Point Theorem. Why fixed point theorems? Fixed point theorems tell us when a function has a fixed point and sometimes even guarantees that is unique. This theorem plays a key role in many areas of mathematics, from solving differential equations to analyzing recurrence sequences. The list of fixed point theorem is very large, and the most famous are Banach Fixed Point Theorem. It's the topic of our video today. It says that in a complete metric space, every contracting mapping has a unique fixed point. And we have a mean to approach this fixed point. I will give you the more precise statement in the following. This theorem has many applications, namely for solving nonlinear equation. For instance, you have Picard-Lindolf or Lipschitz theorem, which prove the existence and uniqueness of differential equation. We have also famous theorem, Brouwer's fixed point theorem, which say that every continuous function from a closed ball in Rn to itself, you take a continuous function from a closed ball in Rn to itself, then it has at least one fixed point. This theorem has also many applications in game theory, economic, nonlinear analysis. The last famous fixed point theorem is Schroeder's fixed point theorem, which says that every continuous mapping from a convex compact subset of a Banach space into itself has at least one fixed point. It can be applied in the existence of solution to integral and differential equation. Now let us state the Banach fixed point theorem. If you have a transformation of a complete metric space that always bring a point a little closer together, it's the meaning of this contraction condition, then no matter where you start, if you start from a point x0 and you keep applying this map, you'll end up to a spatial point, namely the fixed point. And you have even an estimation of how far you are from this point. Mathematically, you need a complete metric space and a contracting map. This means that the distance between the image of 2 points xy is less or equal than k, the distance of the initial point, and k is between 0 and 1 and different from 1, then the theorem tells us that this map, the Banach fixed point theorem, tells us that math has a unique fixed point. This means that this point satisfies if x star equal x star, and moreover, for any initial condition, if you consider the sequence given by x1 equal f de x naught and xn plus 1 equal to f de xn, then this sequence will converge to the fixed point. So in this video I will give you a complete proof of this theorem, but before I will recall what is a complete metric space and what is a continuous function on this metric space, and I will show you that any contracting mapping is also continuous. So the key ingredient, so we need to know what is a metric space, what is the notion of completeness of metric space, namely the equivalence between Cauchy sequences and convergence sequences, and the relation between continuity and limits. Okay, now the definition of a complete metric space. We start by the definition of a metric space. A metric space is just a set A with the distance. Distance is the map from A cross A to R plus, and it is distance. This means that it's symmetric. The distance between x and y is equal to distance to y and x. The separation condition, this means that the distance between 2 points is equal to 0 if and only if these 2 points are the same. And we have also the triangular inequality. Distance xy is less or equal to distance xz plus distance zy. The fundamental example of metric space is of course Rn, which is Euclidean distance given by the square of x1 minus y1 square plus xn yn square. It's the classical distance in Rn. But there are many other metric space. Namely, you can consider the set or the vector space of continuous function on a closed interval, and you can define two distances on this space. The first now is the infinity distance or the supremum distance. It's given by the sup of the absolute value of x minus fx minus gdx. You take the supremum of all the distance between the value of f and g. You can also define distance by taking the square of the integral from a to b of the distance au carré of fx minus gx t dx. There are other distance on this space. So as you can see, there are many examples of metric space, and when we have metric space, we can define a ball on this space, and then we can define open set and closed set, and we can define topology, and hence we can do analysis on this space as we do on Rn. Now, thanks to the distance, we can define what is the meaning of convergent sequence in a metric space. If you take a sequence in a metric space, you say that the sequence converge to a point in A if you have the epsilon criteria. This means for any positive epsilon you have n naught such that the distance between xn and x is less or equal to epsilon for all n this bigger than n naught. And you have also the definition of a Cauchy sequence if for any epsilon there exists n naught such that for any p and q bigger than n naught, the distance between xp and xu is less or equal to epsilon. It's the same definition as when you are on Rn or in R more simple. And the completeness of a metric space means that you know that any convergent sequence is actually a Cauchy sequence. It's a consequence of the triangular inequality, and the completeness say that we have the converse. This means that any Cauchy sequence of A is convergent to a point in A. Okay, so now we have the notion of a metric space and a complete metric space. Of course, Rn mini endowed with its Euclidean distance is complete. It's a consequence of Bolzano-Weierstrass theorem. We have also that the space of continuous function on a closed interval AB with the infinite distance is also complete. It's a consequence of the completeness of Rn. However, when you undo the space with the distance d2 defined by the integral, this is not complete. It's a well-known result. So we have complete metric space, and we have also not complete metric space. Now we have also the notion of continuous maps between metric spaces. If you have a map F between two metric spaces, then F is continuous at a point x0 in A1 if one of the following equivalent assertions hold. You have the epsilon delta criteria, which means that for any epsilon there exists eta such that when the distance of x to x0 is less or equal to eta, then the distance of f de x to f de x0 is equal to epsilon. And we have an equivalent assertion, which means that for any sequence in E1 which converges to x0, the image sequence fxn converge to fx0. So these two conditions are equivalent. if you want to characterize the continuity of a map between metric space. And the second one can be used in general to prove that a function is not continuous. Okay, so now we have, of course, if f is a contracting map, or just satisfy this inequality, then f is obviously continuous by using the second characterization of continuity. Because if you take a sequence which converge vers two points, its image will converge to the image of this point by using this condition. And okay, now we have all what we need in order to prove the Banach Fixed Point Theorem. So let's recall the statement of the theorem. We have a contracting map on a complete metric space. So a map which satisfies this inequality, and we will show that it has a unique fixed point, and actually we will show that for any initial condition x naught, this sequence converge to the fixed point. And moreover, we have this estimate of how far we are from the fixed point. Okay, let's start the proof. So we take x naught in E, and we define this sequence by taking x1 equal to fx naught and xn plus 1 equal to fxn. So the first step is to show that this sequence is a Cauchy sequence, and thereafter, since E is complete, this sequence will converge, and we will show that it converges exactly to the fixed point. Okay, now we will use the contraction condition. We have that the distance of xn plus 1 xn equal, because xn plus 1 is equal to fxn, and xn equal to fxn minus 1. And this quantity is less or equal to k distance xn minus 1, and we can continue that this quantity will be less or equal to k distance xn minus 1 xn minus 2, and by induction we get this formula. So we have distance xn minus 1 is less or equal to k power n minus 1 distance x1 x0. Now by using because we will show that this sequence is a Cauchy sequence, we need to estimate this quantity. So we will use the triangular inequality to get that this quantity is less or equal to the sum from a equal n to p minus 1, the distance xa plus 1 xa. So here we use the delta inequality, and we have also this inequality, so we get that this quantity is, it is, I think that it is the key point in the proof. Now we recognize here a geometric sequence, the sum of consecutive terms in a geometric sequence, and we have this formula. We can take k power n in factor and get this sum, and this quantity is less or equal to 1 over 1 minus k, and we get this estimation. Now, so we get that distance between xp and xn is less or equal to k power n over 1 minus k distance the x1 x0. And now since k is strictly inferior to 1, this sequence converge to 0, so we can make this quantity less than epsilon for n bigger than rank n0, and we get that our sequence is a Cauchy sequence. Now, from the completeness, we have that this sequence converge to a point x star. Now we will show that x star is a fixed point. We have this limit, the f de xn. Now we have seen that f, since f is a contracting map, f is continuous, so we can switch between f and the limit. It's our characterization of the continuity of a map between metric space, so we have this. This is equal to x star, but this one is equal to xn, and this also, this limit is also equal to x star, and we get that f the x star equal to x star. Now to get the estimation, we have this inequality, and we fix n, and we vary p to go to the infinity, and we get, since the distance is continuous, so we get this estimation. And now to show the uniqueness of the fixed point, we suppose that we have two fixed points. We have that the distance, the x star, y star, since x star and y star are fixed point, this is equal to distance fx star fy star. But the contraction condition tell us that this is less or equal to k distance x star y star, but k is strictly inferior to 1. So the only possibility for the x star y star is to be equal to 0, and we have x star equal to y star, and we have done, and this completes the proof of Banach Fixed Point Theorem.